Hi everyone, we're back for our final video on implicit differentiation. This is the final example, example 3. This one's going to be a little bit different from the first two. The first two dealt with right triangles and implicit differentiation. This one's going to deal with a cone, so it's going to be a little bit different. So let's go through it. Let's read it first. Water is pouring into a conical tank. That's a tank shaped like a cone at the rate of 8 cubic feet per minute. If the height of the tank is 12 feet and the radius of the circular opening is 6 feet, how fast is the water level rising when the water is 4 feet deep? Okay, so let's start with a diagram. First thing I'm going to draw is a cone-shaped tank. So let's go ahead and draw ourselves a cone point down. And I always like to put my fixed values on the diagram first. They are telling me that the height of the tank itself is 12 feet. So I'm going to go ahead and call this 12 feet. And they're telling me that my radius of the tank is 6 feet. So I'm going to go ahead and put that on as well. And the water is pouring into this tank. So I'm also going to draw kind of like a generic water level because there is going to be water in here. And that water is also going to have a height that's changing. I mean, this H value in feet is going to change as the water fills, as is the radius. So I'm going to put those two values on because they're part of my diagram that's changing. Okay, I also might just kind of show here the water is pouring into the tank. I don't know what it's coming out of, but pouring in there. Okay, let's start talking about our givens. The first sentence has a given. This water is going into the tank at a rate. The minute I see that word rate, I know it's a given. 8 cubic feet per minute. So something equals 8 cubic feet per minute. And I love the units because it helps me to give it a label. Cubic feet is volume. Minutes are time. So what's happening here is I'm being given a change in the volume in this tank with respect to time. This is how quickly the volume of the tank is changing. So each minute, 8 more cubic feet. Each minute, 8 more cubic feet of water going in. Okay? If I keep reading, we already got this part. The height of the tank is 12 and the radius is 6. We already got that. Here we go with what we're trying to find. How fast is the water level rising? How fast is the water level rising? Well, I've called the water level H. So I want to know how quickly H is changing. So I'll be looking for dH dt in height is measured in feet, time in minutes. My label is always given by what this is measuring and what this is measuring. I'm looking for that when the water is 4 feet deep. That's a given. So when H is 4 feet. So at the exact moment this water height reaches 4 feet, how quickly is that height changing at that moment is what we're seeking to find. Okay, so now we need to write an equation. The equation must involve the diagram and the variables that are in these two sections. Well, what I see is V's and H's. V's and H's. Time, don't worry about. That'll come into when we implicitly differentiate. Well, V's and H's, the only relationship I can think of would be volume of a cone. So the equation for the volume of a cone is 1/3 pi r squared H. And I love that because there's my H, there's my V. I have one problem. This R, I'm not liking that at all. I don't see one piece of information they're giving me about R, which is why I'm creating this title called Side Work. I need to figure out a way, kind of like an optimization. I need to find a way to get rid of this R and write r in terms of h, so that my equation only has v's and h's. So I'm actually going to appeal to your past when you were in geometry, and I actually wrote this definition down in case you've forgotten. Let me turn to that, and feel free to copy this down if you want to. Our side work is going to involve this statement. Two figures that have the same shape are similar. You probably remember studying similar triangles. Now the ratios of the lengths of the corresponding sides will be equal. So if you have two similar shapes, then you may set up ratios of the corresponding sides of those shapes. So how does that relate to our problem? Well, what I'm going to do is my two similar triangles are going to come from my diagram. So what I've got here is 6, 12, and a hypotenuse right there. And then I've got R, H, and a hypotenuse. So do you see the two similar triangles? So if I have these two similar triangles, similar shapes, then I may set up a ratio of their corresponding sides. So 6 corresponds with R. So I'm going to write 6 over R equals 12 corresponds with H. So 12 over H. And if I simply cross multiply, I will have 12R equals 6H. And I want to solve for R. R would be 6/12 H, or if I reduce it, 1/2 H. The reason I wanted to solve for R is because I want H's. I want to be able to plug 1/2 H in for R so that the R disappears. So my new equation with no R in it will look like this. V equals 1/3 pi times 1/2 H squared. There's my R squared times H. And if I clean that up, let's see, I would have 1/3 pi times 1/2 squared is 1/4. H squared is H squared. And then I have my extra H on the back. So cleaning that up, yet still 1/3 times 1/4 would be 1/12 pi H to the third. So that's a pretty nice equation right there. Now look at that. This versus this. This is volume, but it's all in terms of H. So now I will go up here, recopy it. V equals 1/12 pi H to the third. And now I'm going to implicitly differentiate with respect to time. We've got to get the t in here. So moving from left to right, the derivative of v is just 1. But because it's implicit with respect to time, tack on dv dt equals. Now over here, I'm just going to go ahead and use the power rule because 1/12 pi is just a constant. So I'm going to take 3 times 1/12 pi, which will be 3/12 pi, reduce my exponent on the h by 1, so 3/12 pi h squared, dh dt. 1 times dv dt is just dv dt, and I can reduce 3/12 to 1/4 pi h squared dh dt. That's about as nice as I can clean it up. All right. Moving over to our fill in and solve, let's look up here at our givens and fill in what we can. Okay, dv dt, we have that. dv dt is 8, so that's nice. So we have 8 equals 1/4 pi is a constant, so I'm just going to copy that down. Okay, do I have h? Yes, I do, right here. H is 4. So times 4 squared dh dt. Okay? So cleaning that up and solving for dh dt, I have 8 equals 1/4 pi times 16 dh dt. And 1/4 times 16 is just 4, so I can clean it up further and just write 4 pi dH dt. Solving for dH dt, which is what I want to find, I'm going to divide both sides by 4 pi. So dH dt equals, and I'll go to my calculator here again. Alpha y equals 8 divided by, I always forget what I'm typing, 4 pi. 4 pi. 0.637, so 0.637 feet per minute. And again, I already knew what my units were going to be. Okay, now my final statement. Again, I've already written this out for you. Final statement is, when the depth of the water is exactly 4 feet, the water level is rising at a rate of, my answer, 0.637 feet per minute. And that finishes up example 3. So the rest of this lesson, the notes are over, and the rest is just your time to practice. Okay.